And next, I guess you'll get set up. Next, we have Jana Pavlasek, who is an assistant professor at Polytechnique Montreal, who works on robotics, also affiliated with Mila, and I believe also did her PhD at Michigan as well, as Joyce was there too.
These mics always make me feel like I'm Britney Spears. Um, but I'm not. Hi, everyone. I'm Jana Pavlasek. I'm an assistant professor at Polytechnique Montreal. So I represent a little bit more of the autonomous agents part of the theme today, more than the LLM side. But I'll try to make some connections to how I think these topics relate to each other and what we're doing in robotics research. So um, I we want robots to be able to, sorry, there you go, to do all sorts of tasks for us. We want, generalized robot assistants that can do things autonomously in our home, like, cleaning tasks, cooking, maybe kind of assembly and maintenance tasks. And in my work, I'm really interested in these complex, unstructured environments like this one. And so in a lot of our home environments, we want our robots to be like generalized to our real world scenario. We don't have to want to go around like making super clear structured environments for them like we might do in a factory. We have these unstructured environments where things move around and dynamic. They can't be like cleanly expressed. And we have to be able to reason over diverse scenes and diverse solutions and goals. And so this applies to, of course, to home robots. This is mostly, I'll talk about, robot manipulation and assistive robotics applications. But robotics is a really broad field, as you heard from Liam this morning. And so I've worked, I like to apply methods across lots of different applications. So, I've worked in industrial robotics applications, outdoor field applications where we have a lot of, sensor noise, as well as this assistive robotics. I also have some of these problems are also in educational robotics, which I'm not talking too much about today, but I'm always happy to talk about that too. But I'm going to focus on this assistive setting here to talk a bit more about the challenges. And so if we have a robot like this one with, it's got a head camera that has a 3D camera and a robot arm. So we need perception that is reliable enough to be able to manipulate, sometimes quite precisely, any objects in our environment. And this is hard because in like regular scenes, unless you're in a perfect factory setting or maybe your house is like really, really clean, we have occlusions. Normally the thing that we want to manipulate is not like directly visible to us. And we can have complex object models, like we could have non-rigid objects here. These are hand tools, a lot of them articulates, right? Or you could have deformable objects, for example. And if you're able to, handle this perception, you have to be able to actually plan to manipulate these objects. And normally we think that's, pretty simple for humans. It's very simple. You just go and grab objects and manipulate them. But it's very, very challenging for robotics. We have like very high dimensional state spaces, and we have multiple competing hypotheses. So there's these like complicated multimodal distributions. And these, you can also have dynamic scenes. So things are changing as you're planning. Like if you have multiple robot agents in the scene or other human agents, for example. And of course, when we have these two challenging problems of perception and planning, that intersection between them just creates this very, very difficult robot problem. And so my work thinks about how robots can operate reliably in like these real world challenging scenarios, like unstructured and dynamic environments. And so the focus of my work has been on these models of uncertainty and how we can take uncertainty into account in our robot models. And so when we think about, learning models and AI, it's not just about a lot of data and a lot of compute, but it's also about inductive bias, like what's the actual model that we pick. I like to explain inductive bias using this little example. These are two actually mathematically equivalent models of the solar system, which is one with the planets moving around the sun and one with the planets moving around the earth. These both match the data, but one of them is much more descriptive and much more has given us much more power in terms of understanding like orbital mechanics, right? So it's not only about having having good data and matching the data, but having like good models for that data, right? And so I like to think about, and like some of the inductive biases that I will talk a little bit about in my work is having diverse solutions. So I talk about like non-parametric distributions, right, which are you can have like multimodal particle-based distributions. Instead of just like one single solution, we want to be able to think about uncertainty. So with robots, that's a very important signal for us. If we can say we're not sure about where something is, right, we can take like an information seeking action, right, which is something that's like unique in the robots, like embodiment compared to, system that just has a single input output. And so I believe that complex problems need diverse solutions. Like if you have simpler problems, you can have really, really optimal solutions. But in robotics, we're thinking about these very complex problems where you have to consider lots of different alternatives. And the second element of this of the inductive bias that I like to think about is distributed inference. So we can split up our big problems into lots of smaller problems, like by we can think about this in multi-robot coordination, just thinking about one policy for each robot, or in pose estimation, thinking about what the different parts of objects can do. So I want to talk a bit about, I have like 3 chapters that kind of span a big breadth of robotics. So first I want to talk about some work that I did kind of like in the first half of my PhD on perception for articulated objects. And we use this idea of distributed inference to get this tractable and robust pose estimation, specifically that worked in these challenging environments. And so the idea, like pose estimation, is maybe a historical concept at this point, where we want to get we want to actually localize a 6 degree, like a 3 degree freedom position and an orientation. And so when you think about objects that a robot wants to interact with, there's this concept of affordance where, different parts of the object do different things. And this, right, they have different affordances, like in terms of where you can grab it and what those different parts do. And so that model of action can be our kind of idea was to use it within the model of perception as well, and to model this robot by part, or this object by parts, and using this probabilistic graphical model. And at this point, I like to incorporate data-driven techniques, like learned techniques, together with model-based techniques like probabilistic inference. And so you can model, for example, if you have an object like this, a hand tool, we know the geometric relationships between these parts. We call that the pairwise potential, right? So this kind of acts like a prior. But we also, we have a visual image that we can process using to figure out how well, what kind of pose matches the visual image. And so our pairwise potential lets us use this known prior information that is not learned, but that's like background that we can provide, and we can combine this together with a learned unary potential that gives us this fast estimation of these visual, and the ability to kind of encode these complex visual features. And so, we may have this kind of like noisy 2D estimate from our learned model, and we kind of refine it using the prior of our geometric model. And so we used like a particle-based, very classical inference algorithm to do this. And the idea was that because we had the robustness of this classical uncertainty, like inference method, even though you could have like significant occlusions, you'd be able to recover the poses of these objects. So you could have robots manipulate them using this, by adding this kind of layer of robustness. So at this point, this original work that we did is like very historical. It's from 2020, very long time ago. And we were really, relying on knowing a lot about the geometry of the object. And so the work that we were doing after this took advantage of these new models that are implicit rendering methods that can let us use these learned models. We were using NERFs here, and then later on we used Gaussian splatting as well, that let us kind of render hypotheses for objects using a learned implicit representation at any kind of candidate pose, and kind of loosen the reliance on geometry and models. And so I won't go too much into detail into the pipeline and how we did this, but we took the same idea of this parts-based approach to learn individual rendered models and compose them together so that we could have these configuration-aware renderers that worked well with these articulated objects rather than just static objects and static scenes. And so these learned implicit generation representations let us get this high fidelity scene generation, which gives us more ability to get fine-grained detail in how we are going to manipulate these objects. But so I've talked about how we could kind of represent the scene. I haven't talked about how we actually can interact with these objects. So in this next part, I want to talk to you a bit about my work on how we can plan to actually manipulate these objects. And so this body of work, we were really interested in these types of problems where you have a lot of uncertainty over where your goal sets, like where to go in order to achieve your goal. And we were using diverse sets to be able to accomplish these more complex objectives. So if you think about just how you grasp an object, there's many different ways to do this. And the best way to do this depends on the task and depends on the environment and depends on the object, right? And so often when we're doing this in robotics, we just pick, some grasp point kind of with some heuristic or arbitrarily. And this is, leads to a lot of problems and instability in robotics because we have to, that point might not be reachable. This is a really simple environment, but if we have collisions and things like that, that might make it more difficult. And then we can also, the environment can change during execution. So if you pick that point, by the time you get there, that might not be the best one anymore. But actually, in many cases, we don't really care that the robot achieves like a very specific point in 3D space, but we care just that it grasps the object stably, right? But it's hard to model this set. So we rely on data-driven methods to do this, mostly in these high fidelity simulation environments, and with learned implicit models, we can get a bunch of data about what grasps are stable. But then can we actually use these? Then we get this kind of distribution, right? So can we plan if we're looking at this distribution of grasp points? And so that's what we were trying to do in this work. But if we have these diverse, goal sets, we have like lots of places that we could end up depending on the environment. We are also going to have some diversity in terms of our trajectory distribution. So you can actually model these planning problems as inference problems by representing your robot trajectory as a distribution. And that lets us consider multiple possible paths, right? So you could there's different possible valid paths that, accomplish the same goal. So one way we could represent this, like a common way of representing this, if we want to be able to express like the full diversity of the environment, is using non-parametric distribution. So we just have a bunch of candidate paths that kind of make up a distribution. And so normally if I say, all of these words, you might think about sampling-based methods, and that's the kind of common way of solving these problems. But they tend to, in theory, they can represent any type of distribution, but in practice, they tend to collapse and actually struggle to represent that diversity. And in this particular example, we have like this diverse set of goal sets. So what's the point of having all these, saying that we can represent our goal that's in, where there's multiple different grasp candidates if you don't have diverse trajectories as well. So there is this recent method, well, it's recent by statistics, statistics standards. It's from 2016, a little less recent by, LLM standards. But it's called Stein variational inference, which models a distribution by kind of updating this particle set. And so this is a really nice method in our context of being able to parallelize things on GPUs and being able to use learned likelihoods, because it only relies on having like a differentiable likelihood, and it's a really easy algorithm to implement and parallelize. And its kind of key features is it's really good at using this. It's really good at maintaining modes because it has this kind of repulsive force between particles. So this paper came out and a lot of roboticists got excited about it, and there were a lot of different applications to it in robotics. And so one example is using it for this path planning problem, because you can actually get these really diverse trajectories, which is like if you've ever played with these sampling methods or in robotics or otherwise, is very hard to achieve and really just works very magically out of the box with sign. And so our goal for our problem was to find a set of trajectories that don't terminate at one specific point, but that just terminate in like a distribution that could be like the set of valid grasps, for example. And so this, I've been talking about grasping, but there's other examples too, like user preferences for a task, or like semantic goals, like the type that Joyce was talking about in her talk, right? Like go to this room or go to this type of object, right? Where these are kind of distributions. It's not like a point in 3D space, but it's just a semantic goal. So while it's often easier when we have these more abstract goals to generate samples than it is to model them explicitly. So there's been a lot of work in high fidelity simulation for things like graph generation, but you can also use LLMs to give us these types of goals. So we have a planner called the goal set planner, where we use a bunch of, a set of potential goals that we model. And we are able to kind of plan to all of them at once, which is nice because if the environment changes or something, we can update which one we are going to. And we're basically trying to, the idea of it that I won't really go into is that we try to match the terminal states with these goal distributions and using like some clever statistics. But so the stable grasping was one of our primary interesting use cases, because these are hard to represent analytically, but we have a whole bunch of these data sets of these representations of stable goals. And of course, when you're in a robotics lab, you always need demonstrations on real robot hardware. So this was work that I did while I was in the NVIDIA robotics lab. So this is the robot that they have over there. And so, like I said, it's not, grasping, I think, is a great example and very common example in robotics, but there's lots of other kind of examples of these types of goals. So in this example, it's like a simulated table setting task where, as you're setting the table, then the environment kind of changes. Like now there's some region that's in collision, and so you have to go to the kind of backup region. And so we don't have to add any sort of heuristics or anything. Our method can just kind of use these grass points to plan end to end based on what the environment is. And so for us, the takeaway was that if we are using diverse goal sets, then we can plan in a way that is more scalable and lets us consider these more complex planning objectives. And so we always in robotics like to make our lives more challenging and work on more and more interesting problems. And so the last thing that I want to talk about is how we could take these kinds of same approaches and apply them to conditions where we have situations where we have many robots and multi-robot coordination. Where we also want to see whether our hypothesis of like these diverse solutions can give us more adaptable planning in dynamic systems. So just a brief primer on multi-robot planning. If you have a bunch of robots and you want to control them, you can optimize over the space of all of the robots, and you can find one, kind of treat it as one single problem, get the state of all the robots, do your optimization, and then send back your command to each one individually. This normally gives us really nice optimal solutions, but you have to actually have communication with your robot. So if you're outside in a really big space, like wildfire monitoring or something like that, you may not be able to do this. And also it doesn't scale well. The larger it gets, the harder your planning problem is. And if you're adding and removing robots, you're going to have to keep reinitializing your planner. And so it doesn't scale super well. So there's the other way of doing this is to do it decentralized, where each agent has its own policy that it uses to pick the best action, and it can still pass information from its neighbors. And so this scales better to large swarms, and it has our nice property that it factors the problem into lots of smaller ones. But these methods, there's a lot of methods for doing this, and they tend to have the problem of deadlock. So deadlock is like if you're walking down a hallway and you see someone coming the other way and you're both kind of moving back and forth the same way, and you can't decide where to go. So that's what happens with these robots, and these robots are trying to cross a fairly simple narrow hallway example, and this is a fairly good baseline for these methods, and they kind of get stuck like this. But so if we are able to consider like the uncertainty in where your neighbor might go and consider the different paths the robot might take and kind of optimize over that, then we actually are able to solve this problem a lot more smoothly. So this is with the algorithm that we developed based on the similar planning work, but applied to multi-robot settings. So since we want to consider uncertainty, we like to model things probabilistically. So the robots are in a graph where the edges connect whoever is in communication range. And we made this algorithm that we called Stein variational belief propagation that does inference on graphs. And so this is applied to what we might call like a robot localization challenge, where you're trying to localize based on your known, like your neighboring robot's localization. And so you can see we get these really nice multimodal distributions. In this case, we have a bunch of multimodal perception uncertainty, but we can still kind of recover the true position while maintaining a sense of the distribution of where the robot might be. And so since we are using the Stein method instead of like a sampling method or an optimization method, we don't get a collapse to local minima. We get a more we maintain the distribution more accurately, which lets us actually get more accurate localization. And because it has this ability to maintain modes, it's actually a lot more particle efficient than if you wanted to do something like a sampling-based method. So even if you use quite a small number of particles, you can still do as well as a sampling-based method with much or better than a sampling-based method with many more particles. And so what we really were interested in is doing this with a multi-robot coordination case. And so you can see that, especially at the beginning, once it gets to the end, the distribution is pretty unimodal. But when there's lots of obstacles and lots of other robots involved, you can see there's kind of these nice like splits in terms of where the robot might go that it continuously updates as it moves along. And so it's much better at avoiding these deadlock scenarios. It doesn't really get stuck the way that these more traditional, controllers that don't really consider any source of uncertainty do. So if you let them go really close to each other, they do get there, but they do it pretty slowly and they do kind of bump against each other, which is fine in simulation, but not great on real robots. And so again, as roboticists, we always like to put things on real robots. So these are small little robots that are Raspberry Pi based, and I use them for teaching. And so they have very noisy perception and very noisy mechanical models. They're not anything super sophisticated, and they just have a Raspberry Pi. But we're still able to run our method. We use a small swarm because they're just Raspberry Pis. But it's still fast enough to run on this, and it has quite a lot of noise in this perception and the action models, but it still is able to localize, to work pretty well because it's inherently considering this uncertainty. And so these diverse systems let us have these more adaptive planning in our dynamic multi-robot systems. And so my group at Polytechnique is looking more at these types of multi-robot problems, and we're really interested in how we can use, we were doing collision avoidance before, which is fairly easy to express analytically, but there's a lot more interesting problems to do with maneuvering where the physics are much more complicated, right? If you're pushing around objects and maneuvering, or like a joint payload carrying robots. And so we're looking at how we can use different learned models to capture that physics information that's not so easy to express. And we're also looking at how you can scale to these larger dynamic grasps if we have even more robots, or if we want to solve different types of robot problems like SLAM and mapping. So those are the main things that I wanted to talk a little bit about, but I'll kind of end by wrapping up and talking a bit about some future work that we are looking at in my lab. So so I want to go back to this question of the best inductive bias in robotics. I think we have to think about our models not just in terms of getting more data and throwing more data at the problem, but what are actually good inductive biases to pick for our robots. And so I've done a lot of traditional uncertainty based methods especially in my PhD, and I believe in this theory that if you have these complex problems, you really need this diversity in your solutions to be able to adapt as things change in your environment. But I think that, thinking more about what the best models to use are that represent well our 3D space, not only in a chatbot interface, but that represent the 3D world and collisions and the dynamic nature of it is important. I think that there's a lot of interesting work that's already kind of going on in grounding machine learning models in probabilistic methods to be able to capture these methods that have been so differentiable versions of these methods that have been very impactful and successful in robotics so far, but that only get us so far if we have to model them heuristically. And I think, if we can make more of these models differentiable, right, with these tools like this sign inference, we can enable more learning-based methods that'll let us deal with more complicated problems. But it's still very useful to be able to plan and reason over these models when we get to the really low-level important stuff, like not running into things and running into people. And so I think these like learned models still need to be able to be planned over and reasoned over. And I really like to focus on these real world unstructured environments and real robots in these challenging environments, and making sure that we're pushing the limits of these models and thinking about how they can apply to these different applications. So yeah, I know I'm standing between you and your lunch, so thank you for your time today, and you're welcome to reach out to me if you want to talk more about robots, and I'm happy to take any questions. Thanks.
Yeah, this is really cool work. Does anyone have a question? If so, could you go to the mic? Okay, so I really think the Stein belief, the Stein variational inference thing seems like really interesting. Have you seen anyone apply this to, like, for example, sampling from a language model?
So yeah, I think that's a really interesting problem. Uh, not, I haven't seen any specific papers. There might be that I'm missing. But so when you're doing this optimization, I think one of the things that, I've been talking about with people in my lab is that the gradients in these language models, we have these really interesting kind of 3D models, but sometimes the gradients are actually quite unsmooth. And so it makes it hard to use those learned gradients to actually plan over, so I think that that's one of the big challenges if we want to kind of merge these two methods. And I think there's lots of interesting things to do at the intersection of those problems.
Cool. So yeah, if there's no immediate questions for the whole audience, we, I guess, have a couple minutes before the official lunch break where we can all have like a little bit of discussion. So please feel free to talk to any of the speakers who are here or your seatmates or whatever. Thanks.